Alright, so I think this is recording. As long as I have electricity. It's thundering pretty bad, and we've got a pretty bad storm out there. Alright, so we're taking a look at Scale Packet 5, which is exponential functions and log functions. And here in this homework, we're working with at least these first few problems with properties of logarithms. Logarithms and exponential functions are inverses of each other, and anytime you have two functions that are inverses of each other, you switch the x and y, you switch the domain and range. So I already know from previous material that the domain of exponential functions is all real numbers, so that tells me that anytime I see a log function, and this ln is just a natural log, that my range is all real numbers. If I have just a single transformation on the domain, a shift to the left or to the right, I just look at it and just see where it goes. But here we have two transformations. We're going to shift it to the left 2 units, but we're also reflecting it across the y-axis. So this 2 minus x, always set it equal to 0. Solve this for x, and that's 2. Now, if this negative sign was not in front of there, I would sit there and say, well, it's 2 to positive infinity. But that negative sign has reflected my graph across the y-axis. So it's on the left, it's coming from negative infinity to positive 2. That's my domain. So you have to be very cautious when there's a negative sign in front of your variable x. Now, the vertical asymptote is a line. I always need to give an equation. Vertical is x equals, horizontal is y equals. So this is x equals 2. When you get that domain, you kind of get this vertical asymptote for free. To find the x-intercept, we need to let y equal 0. So we need to solve this logarithmic equation here. So on the right-hand side, I see two terms. My variable is x, and in that first term, it has my variable of interest, so I need to get that term by itself. Alright, so I need to subtract 3 from both sides of the equation. When I subtract it over here, that cancels, and 0 minus 3 is a negative 3. So now I see that I have 5 times the natural log of 2 minus x. On the right-hand side, I have two factors. The factor that contains my variable of interest is this natural log of the quantity 2 minus x. I need to get rid of that 5, so I'm going to divide both sides by 5. So I'm going to write this ln over here. And you know what? Instead of ln, I'm going to help you out to recognize that this has a base of e. And I'm going to write it as log base e of this 2 minus x is equal to this fraction negative 3/5. Alright, so I've gone as far as I can go with this log equation, this equation in logarithmic form. I need to convert this log form to exponential form. The base of this logarithm is e. Now e is like pi, it's an irrational number. If you go to the calculator, you know, our calculator can estimate pi for us. Okay, I'm only on 3 decimals here. If I put it on float, it will. So here's pi to about 9 decimals. Well, if on the ln button here I have e, and if I just raise the e to the first power, this number e is an irrational number like the number pi, only it's 2.71828 blah blah blah. What's amazing is that pi is comes a definition from geometry, the ratio of any circle, its circumference to its diameter. But this 2.718, that's actually man-made. I think Euler was the first mathematician. There's a formula that gives us this 2.718, whereas pi, we use formulas to estimate it, but the exact value of pi, like I say, it's a geometric definition. So that's amazing to a lot of mathematicians, and if you Google that, get on a sidetrack while you can spend years and hours and years and stuff like that studying that, but something to think about. Anyway, let's get back to this problem. This base of e. this e has an exponent, and the logarithm equals an exponent. So my exponent on this e is negative 3/5. Well, that equals my argument 2 minus x. So if I add x and subtract this e to the negative 3/5, there's my x-intercept. Now, it's going to be pretty hard to plot that point on the x-axis without getting a decimal approximation. So let's use our calculator to that's what we would refer to as the exact value. But if we go to plot the point on the x-axis, we're just going to want a decimal number. So let's come in and take 2 minus this e, and our exponent is negative 3/5. So I claim that just to 2 decimals. My gosh, I doubt if I can graph it by hand much more accurate than 1 decimal. 1.45. Like I say, I'm really just going to call that 1.5 if I go to plot a point. Alright, so x equals 1.45 is good enough. Hope that helps, and I'll talk to you later.